the day today. The only thing we're going to talk about today is your midterm, which is tomorrow, right? Good. You're just trying to trick me now. No, your midterm is tomorrow. It's in a ridiculous number of rooms in RCH. The seating is now assigned, so you can go on Odyssey and check where you actually need to be. At least it's not on Halloween night, right? So that could be worse. That's a night where you could probably have a midterm that's almost guaranteed to get the power turned out or some other ridiculous hijinks, I'm sure. All right, so how today is going to work is I have some review slides. I have posted the review slides to Piazza, so you can open them up and you can follow along. It's kind of going to take the format of, we'll go over a topic, there'll be some questions, I'll give you an opportunity to try the questions, and then we'll actually take up the questions. A few of you have sent requests for content to be added. I have added the content to the slides, with the exception of one solution because I was too lazy to actually draw it out. It requires like this big tree diagram, and I didn't feel like doing that at like 2 this morning, so we'll draw it on the board instead. Maybe I'll take a photo of the paper version and like post that or something. That would be significantly less work. Before we actually get into the slides themselves, just to let you know what the coverage of the midterm is, because I'm sure some of you are going to be like, wow, I should probably start studying for that, you know, like 12 hours before the actual midterm. What did we do in OS so far? Yeah, I remember how it was. Okay, so we are covering everything up to and including multi-level paging. So that's roughly slide 30 of my course notes. I'm sorry, I don't know what that corresponds to in Allie's course notes. Someone has actually made on Piazza a lovely list of topics that are totally coverable. Yes, that's a great list. Thank you for making that list, whomever you were. But before we get into that, I want to point out again some of the resources that you actually have available for you for studying in case you haven't managed to find this yet. So if you are on the course website, please do click on exam information because of course it tells you, when your exam is and where to go. But also under study aids, you'll see this sample exams with solutions. And it's got a whole pile of them. Yes, there are some missing. And yes, there are some solutions that are missing. Unfortunately, we haven't been able to dig up those solutions yet. When we can, we will post them, but it's probably not going to happen for tomorrow. I have also posted the other 2 2019 exams with their solutions to Piazza. Yes, I realize somebody pointed out that I uploaded both blank copies as being the exam plus the solutions. I fixed that now. The solutions are now uploaded and the exam as well. Yes. I don't have fall 2018 at all because I was not teaching the course, so I don't have that content. But everything else we've roughly got. Point is, you got lots of resources here. Use them. I would avoid things in the 2013, 2014s and below because in, I think it was fall of 15 or fall of 16, we actually made some pretty major changes to the course. We took a lot of content out. And so you'll see that the exams seem a lot harder if you go back far enough in time. And if you go back all the way to like when I took this course, you might notice that we have proofs and stuff. Yeah, we don't do proofs. Not anymore. So yeah, lots of things for you to study from. There's a few more posted to Piazza. And then if that's not enough for you, there's the review questions here. These are created by students. Some of them don't have solutions. Some of them have mistakes in the solutions. Again, this was a bunch of students put this together, and we're just sharing it at your own risk. Again, if you're looking at these samples, please note, if you see the word nachos, run. We don't use nachos anymore. We haven't used nachos since I was an undergrad. Someone in 2014 found some of the questions which were relevant, so there's a list there. My one request is, if you have a question about one of these problems or about a previous midterm problem, don't just say question X in the review or question X on exam Y. The problem is a lot of us are actually like answering your Piazza posts on like a cell phone, and while you might be capable of sitting there and typing as fast on a cell phone as some of us can type on like a regular full-size keyboard, I can't do that. And I don't really like using a cell phone in the first place. So please, what I'm asking you is don't tell me to go find the exam question. I don't have them memorized. Actually post the question and the solution so that I don't have to go searching for them when I am doing whatever I'm doing tonight. Yeah. That would make our life a lot easier. All right, are there any questions about just general midterm format and so on?
I noticed that in some past midterms, when you were asked to draw a stack, there are some stack forms that are optional, and some are mandatory. Do we have this kind of stuff?
Yeah, so when it comes to drawing the stack, I tend to be very particular about it, and I don't like to give any leeway. And so that everybody understands that they're supposed to draw every single stack frame, if we ask you to do that, we will specifically say, with respect to OS 161, which should clue you into, hey, I need to be using the stack frames that are for OS 161 and I shouldn't miss any. And yes, in the past we have been a little bit more flexible about it, but we have not been recently. Anything else? If you're curious about the format, like what kinds of questions, the exam looks like every other midterm. Because we take the LaTeX from the old one, and then we just dump new questions into it. And we're too lazy to change the format because it's too much work. So you can expect that there's going to be some kind of short answer questions, there'll be some calculation-based questions, and then there'll be some questions that involve a little bit more thinking. The one thing I will say doesn't show up is I'm not going to ask you to write 200 lines of code to resolve the traffic intersection problem as like some 4-page thing on the last part of your exam. Yes, that has shown up on previous midterms. There's a reason why I don't put it there. It's because every time that shows up, it takes us over a week to mark it because it's a nightmare, and I don't want to mark it. So we're just not going to do that. We can ask you questions without making you write 200 lines of code and us take an entire week to actually grade it. So I don't tend to ask long coding problems, but you can expect some coding, just smaller things. We are not checking your C syntax. So this is not CS136. If you're missing a semicolon or a bracket, I really don't care. It's mostly the idea I want. And I mean, realistically, you can write pseudocode in any language you want, but I would advise against using languages like Lambda or Prolog, because I'm the only one in the team who actually speaks those languages, and yeah, you're just going to confuse everybody. Yeah.
What is meant by turnaround time on the board, on the PowerPoint? On the projector, sorry.
What?
So it says, note what these questions refer to as response time is what the current note is called turnaround time. I have no idea what turnaround time means.
Yeah, because we haven't done that in like 10 years.
Okay.
So don't worry about it. Yeah, you don't need to worry about that. If you see terms and you're like, what the hell is that word? There's a pretty good chance we don't do it anymore. All right then. Let's go over to the midterm review problems then. I think I almost went over to the networking slides, but that's not going to help you any. All right. So, what did we start out with? Well, we started it out by talking about what is an operating system. And it's kind of hard to actually pin down a particular definition for an operating system, because if you look at what an operating system has been through history, its definition has changed. So when we're talking about modern operating systems, remember we're looking at things that are creating execution environments for the program to run and then loading and running those programs. We're looking at things that are abstracting all of the hardware and the different resources of the computer for the user programs. And we do that for two reasons. One is the security. Another one is, well, we need some way of fairly sharing them. And the third reason is it's good design to actually abstract things. Because when we make changes to the operating system or the underlying hardware, I don't want to have to actually change each of my user programs to reflect the fact that the OS made a change, or reflect the fact that I put a new graphics card in. The operating system is also generally today going to provide you with a lot of common utilities and libraries and little programs. That's things like I/O libraries, your system call libraries, so that you can actually interact with the abstracted hardware. You're also looking at things like shells, desktops, and so on and so forth. And another thing that a modern operating system does, which you should be intimately familiar with now that you've done A2A, is the fact that operating systems are responsible for responding to all interrupts and all exceptions and actually handling them. So, if we take a minute just to think about this question, I want to know, why might an operating system abstract how data is stored on the disk?
Security.
Security. Any other reasons?
So that processes can't interact unless we want them to.
That's kind of a part of security, right? So
Okay.
It makes development easier to separation of concerns.
yeah.
Future updates, if you update something, say on your Mac, that goes from OS 32 to 64-bit only. Actually, maybe not something like a good example, but for future updates, you don't have to worry so much about the processes you're talking directly to the files. They can instead just call libraries.
Yeah.
You can have more virtual memory existing in processes than that actually exists on the disk.
It's not quite why we abstract how the data is stored on the disk, but it is a true statement all the same.
We can change how the format of the data we store on the disk.
That's also true. So you've all given lots of very, very true things, but the big idea is security. So if we didn't have the operating system as a mediator between the user program and the actual way that files are stored on the disk, then how do we uphold permissions on those files? Because you're the user program, and if there's no operating system in between that's checking to see if you have permissions to access the file, then we leave it up to the process to say, hey, do you have permission? Of course the process is going to say yes. So for security reasons, for isolation reasons, we also want the operating system to do it. The other thing is, when you actually write data to a file, you don't have to think about what is the file system, what is the disk I am writing to. Am I writing to a refrigerator-sized tape machine? And is it running, an 8-bit file system? I don't even need to worry about that. I use the command write, and the operating system actually takes care of how those individual bits are actually stored on that physical media. And I, as the user, never have to worry about the actual physical implementation of that file system. So, good things happen. All right. So after we talk about what operating systems are, then we started moving into our discussion of threads, which obviously play a huge role in operating systems. And probably also your nightmares as you've been trying to debug A2A. So remember that every thread of a process is sharing that process's address space. So threads have shared access to the code and to the heap and to the globals of the process to which they belong, but each thread actually has its own stack. And for the sake of discussion, we also say that each thread not just has one stack for the user program to put its stack frames. We like to say that each thread actually has two stacks. And the second stack is where the kernel is going to actually execute. So we have a user and a kernel stack. Now, why do we actually use threading? Well, because some programs, it's just easier to express them in a multi-threaded nature. Sometimes we have threading, or at least the threading came to be to give us better utilization of the resources of the system, because many programs are going to stop and wait for things to happen, like data to go on the screen, data to be written to a disk, or you're waiting for a print job to be finished. And you don't want the CPU to be idle. So by having multiple threads, we allow us to do multi-programming, which means that when the CPU is idle, we're going to choose another thread to actually run. And with threads, if our hardware actually supports it, we can actually get significantly improved performance by actually letting threads execute in parallel. And even still, we can give the user the illusion that the threads are running in parallel by doing time sharing, which is rapidly switching between the threads such that in a large unit of time, everybody is going to make some progress. So threads are pretty important things. Yeah?
Can you elaborate on the distinction between multi-threading and multi-programming?
So multi-threading, we usually are referring to multiple threads physically running in parallel, whereas multi-programming is just one program was running but became blocked, and so we chose another program to run.
So like the level above, sort of higher level version of multi-threading contributes to
It can. Yes. All right. Now, with respect to OS 161, thread fork is used to create a new thread. And remember that when you are calling thread fork, that you have to tell it which process you want the thread to be attached to. Hopefully, you're very familiar with that right now. If you haven't started A2A yet, the deadline has passed. But of course, we're going to retest all of A2A on A2B, so maybe you should start now. So the other thing that's important that we pass to thread fork is the address of the entry point function. That is, what is the address of the sequence of instructions you want this new thread to actually execute. Then we have thread yield, which remember, that is going to cause the thread to voluntarily give up the CPU. Now what's interesting about thread yield is it's not a guarantee. You can call yield, and in practice, like on the computer sitting in front of you, due to the sheer number of threads that exist, there's a pretty good chance that if you call thread yield, you'll give up the CPU. But it's not a guarantee. If no other threads are running, or you are still the highest priority thread that exists, then even though you have voluntarily asked to give up the CPU, there's a good chance you end up running immediately again anyways. Yeah.
So in the state diagram, when you call thread yield and it stays running, does it move, does it just stay in running, or does it move to ready and then immediately get dispatched back to running?
So that's an interesting thing, and that really comes down to the implementation of yield in the operating system. So if you, I think if you actually look in OS 161, and I have not looked at thread switch in a long time, but it actually checks for some of these different cases and may avoid calling switch frame and all of that garbage, because there's no point. Just send it back. Yeah. So a lot of OSs would do things like that. All right, the other function that OS 161 provides you is exit, which if you call it, it immediately terminates the calling thread. Some other things to remember is that threads don't have relationships. There's no concept of parent thread or child thread or sister thread. It's just a bunch of threads. Just a bunch of threads. And yes, there are other thread functions like join. They just don't exist in OS 161. So here's a little problem. I'll give you a couple minutes to try it. And in this one, what you have to do is we are going to call this function with null and 0. And I want to know how many what gets printed, not how many threads there are. What is going to be printed when this function actually gets called? Now I know you're not going to sit there and actually draw out every possibility, but just think about what are the possibilities, what are the rules about printing this. For anyone who wants a seat, there's 2 over there, and there's 1 over there.
Okay.
One port, we get 3 frames. But you always have to have one.
You don't have that's one life.
There was one that was like, it was very and then every single question like, how do you consideration it's just it's really completely wrong. But it's just the same as the first
All right. Anyone have any idea how this might show up?
Start with a 0.
Yeah, that's pretty good.
Yes. And then 2 threads will fork with 1s as their I value, and then from those 2 will fork 2 each will fork 2s, and then basically twice as many threads will come out with the following integers. So before any 2s are printed, you need to see at least 1 1, and before 3 or more 2s are printed, you can see 2 1s, and then you can kind of continue with that. For every pair of 3s, there needs to be another 2 that's printed because the 3s are after 2.
Yep. So for those of you who didn't hear this gentleman here, we can't actually have you output all of the answers onto the page. Because you'll be there for a really, really, really long time trying to figure out where all the context switches happen. But there are some rules. We always start with a 0. You will get 2 1s, 4 2s, and 8 3s, and nothing beyond that. The other rule, of course, as you say, is that you have to have 1 1 precede every 2 2s and 1 2 precede every 2 3s. So that's generally the rule for this particular problem. Now, how did we arrive at that? You need to be paying attention to things like, what is the stopping condition? At what point do I stop forking threads? The other thing you need to pay attention to is, where do I print versus where do I fork? If you print before you fork, you're going to get very different results than if you print after you fork. And if you don't believe me, modify this and just trying to think about what are the different ways, outputs that I can get if I print after I fork. All right. So after we give you threads to improve CPU utilization, give us better program encapsulation, improve our performance, blah, 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 all those fun things, the problem was we gave you just enough to get you in trouble. Because now we have a problem where you have multiple threads for reading and writing a shared variable at the same time. We have what's known as a race condition. And a race condition, remember, is what happens when the output or program result is dependent on the order of thread execution. And unfortunately, this is out of your hands, because interrupts and exceptions are happening all the time, and while you, as the programmer, probably put many of those exceptions in yourself in the form of system calls, the rest of it you didn't, and you have no control over. So when we have a race condition and we have this region of memory that multiple threads are reading and writing at the same time, we call it a critical section. And to solve the problem of a critical section, we want that locking door mechanism. Because you don't want to be in the washroom while somebody else decides to come in. You want it all to yourself. So we created locks to actually protect that critical section. But before we give you the lock implementation, we actually gave you a spin lock implementation. And the reason why we needed the spin lock implementation is in order to have a generic, efficient implementation of a lock or some kind of mutex, as a device that gives you mutual exclusion, we actually need to take advantage of things that are offered by the hardware because we need an atomic test and set. And it is not efficient to do that in a high-level language like C. We really want the CPU to give that to us. Once we've built the spin lock, we can use the spin lock to build locks. And that's actually the neat thing about synchronization primitives. We start with our assembly instructions down on the CPU, and then we build the spin lock on top of that, and then we use that as a building block for other things. These all become little building blocks to build more and more sophisticated different synchronization primitives. Now the difference between a spin lock and a lock. A spin lock will spin. That is, if you try to acquire a spin lock and it is already owned, then you are going to sit there and you're going to keep knocking on the door until that lock is released. And the problem, of course, with the spin lock and you sitting there and spinning and knocking is the fact that you are wasting time. You are using the CPU to effectively do nothing. And which is why many implementations of spin lock, when you acquire them, actually disable interrupts and exceptions. And the effect that that has is that while that spin lock is owned, things like preemption are not happening on that particular CPU, which means that you have uninterrupted access to things while you own the spin lock, and nobody can try to get it from you. Unless, of course, you have multiple CPUs, in which case they can. Now, the difference with a lock does not spin, a lock blocks. So we show up at the bathroom, we see that the door is locked, and instead of sitting there knocking on the door like a total asshole, we're just going to say, oh, look, the door is shut. I'll just go to sleep. Please don't fall asleep on the DC floor. Yeah, don't do that. Now, there are other things that we can do other than providing mutual exclusion. Sometimes we want to control access to resources. So for example, there are 89 seats in this room, which means technically speaking, only 89 threads, you're all threads now, can come into this room and take a seat. So we have a synchronization primitive called a semaphore that can be used to monitor the number of available resources. It has a hidden counter, and when you P the semaphore, you are asking, do you have a resource available for me? And if it does, it decrements its counter to indicate you are taking one and lets you enter. If, however, you arrive and there's nothing there, you go to sleep. Just don't fall down the stairs. Now, semaphores, what's interesting about them is the basic implementation of a semaphore that's provided by OS 161 can actually be used for many, many different purposes. And in fact, semaphores can be used for all different kinds of purposes. You can have a semaphore behave as a lock. That is a semaphore that you create with one initial resource. And as long as you treat it like a lock, always Ping before you V, and never V more than once, it will behave almost like a lock. Is there a difference? Yes. Locks have a concept of ownership because you don't want somebody else to actually, unlock the door on you, whereas semaphores don't care. They don't keep track of ownership. You take and return resources. It doesn't care who stole your laptop. It just cares that it got returned to you. So if you're going to use a binary semaphore, you need to be careful of that. We also have a counting semaphore, which is a semaphore with an arbitrary number of resources. And we also have a barrier semaphore, which is something that we use to implement thread join behavior. We can use the semaphore to effectively have one thread wait for other threads to finish. And if you look through OS 161, they've actually used barrier semaphores everywhere because we don't actually have a thread join to give us the same functionality. And of course, the last synchronization primitive that we have is the condition variable, which remember is used in conjunction with a lock. And the idea behind a condition variable is I'm in a critical section and some condition needs to be true, but it's not. But unfortunately, the lock that I own is specifically for the very thing that the condition isn't true for. So the problem is, I can't own that lock and wait for the condition to become true, because it'll never become true, because nobody else could acquire the lock to change the condition so that I can proceed. So a condition variable lets us simultaneously fall asleep, release the lock, which lets some other thread change the condition and wake us back up, and when we finally wake back up, we own the lock again, and we can proceed as if nothing happened. So 3 primitives. Are there more than that? Yes, there's absolutely more than that. And if this is a topic that interests you, there's CS350, the Concurrency course, which I'm sure you've seen on Reddit. Everyone is like struggling with the assignments. I remember those assignments. That course, by the way, actually used to be the prereq to this one. A long time ago. But yeah, highly recommend that course if this is a topic that interests you. All right, so here we have a quick little problem. So we have a thread that needs to wait for some variable to be less than 100 before it's allowed to proceed. And that variable is a global shared variable. So using only a lock. I know you see this and you're like, oh, we need a condition variable here. No, I want you to use just the lock. Solve it. Take a couple minutes and think about it.
Is that the point where you put yourself out?
Yeah, that's just sad.
But like,
Doing it right.
All right. Anyone have any idea what the big thing is you're going to need in order to implement this?
You essentially do what's inside a control variable, except outside of the other channel, where you simply just apply the lock check, while it's less than the condition, release the lock, grab lock again, check for that again. If you want to do it over and over until you the condition fits, do whatever you want to do.
That's exactly right. Take what's in CV8 and stuff it here. There you go. While the condition is not true, release the lock, acquire the lock again, and when you finally leave the while loop, hey, cost is the value that you want. Now, interestingly enough, we could improve the performance of this just slightly by putting a yield between release and acquire. And the reason why that would improve performance a little bit is if there is a good chance that the yield succeeds, then what you would be doing is you would be letting another thread go, and that other thread may, not guaranteed, may be the thread that changes the condition to what you want. Otherwise, it's kind of pointless because if there's no actual context switch between this release and acquire, you could be actively spinning here doing this a lot, so the yield just increases the probability of the context switch happening. such that the condition can actually change. The point of this whole problem being here in these notes is I wanted to show you that we often give you synchronization problems and say, look, we solved this with this method, with CV and lock. Take it, and now I want you to solve it with a semaphore. Because in almost every situation I've ever come across, whatever it was solved with originally, you can switch it to one of the others. Yes, you may have to massage the code a little bit, add some looping and stuff, but they are very much interchangeable in most situations. So if you want some experience with this, some of the previous midterms have it, or you could look at some of the synchronization problems we already have and ask yourself, what would I do to change this? And if you want a real challenge, take your traffic simulation problem, which you all hate, and use only locks. Just locks. You don't have to meet the performance requirements, but no deadlock either. No deadlock, no accidents. See if you can switch it over to using just locks. I'm not saying it's easy. I'm just saying it can be done. All right. Now, something we didn't talk a lot of, but I did mention it very briefly, was this concept of cooperative concurrency. So this is actually the kind of concurrency that was used in old versions of Apple's macOS, and also in older versions of Windows, the DOS era. And effectively what it does is it doesn't use time sharing, so it doesn't have preemption. So context switches are only happening on exit, yield, and block. So the question is, can you still have a race condition within this model?
So technically, if the compiler rearranges or the CPU rearranges code, or you're like bad at programming, something stupid, then yeah. But I think it's a lot easier to avoid race conditions.
No, that's not the easy one.
I mean, if you only, since you are always in control of when a context switch happens, if you only do so when you know you're not in a critical section, then I guess you could lessen the chances of a race condition.
But even if you were in a critical section, the test and sets would all be done.
If you have multiple CPUs and they both be accessing the
That's exactly right. The answer is yes. You still get race conditions because we haven't said anything about what happens when you have multiple CPUs. And yes, even back in the 80s and 90s, we had multiple CPUs. One of my very first computers had 2 CPUs in it. It was awesome. Except for the fact that who I bought it from had put a bunch of wires soldered across the motherboard. And I don't know what they did.
Yeah. Technically though, like these two answers will still work on a midterm, wouldn't they?
I probably wouldn't ask this. Yeah.
If you were to ask something like along these lines, would you specify the number of CPUs?
We would make it a little bit more clear.
Okay.
Yeah. Yeah, that's something I'm working on, is making sure there's less ambiguities in the questions. That way I don't have to get out of my seat as much. Yeah. So let's suppose you had just one CPU with one core. Because you are in control now, completely in control. Yeah.
But like you get the CPU optimized on volatile variables and then
Why do you need volatile though?
Pardon?
Why would you need it now? Because the only time we get a context switch, the only time, are when you call exit, when you call yield, or when you block to print to the screen or write to a file.
Sure,
These
but
are
if
all
you
things that you explicitly did.
If you store the registers, the variables in registers, the CPU might optimize that and
It won't affect anything. It's that volatile optimization only comes into play when the same or you get a variable that's optimized into a different register in two functions that can be executing at the same time. And since we don't have that on a single core, single CPU, cooperative concurrency system, doesn't matter. I don't remember what I said.
Something about volatile only comes into play when you have.
Yeah, so volatile, what volatile is doing is the optimization that causes, one of the optimizations that causes a problem is you have two functions that are both accessing the same shared variable. The compiler doesn't know that those two functions are going to execute at the same time, and they have the potential. So when we do the register allocation optimization, for the one function we put that variable in register 8, and the other one we put it in 10. And the problem is if those two functions run at the same time, which register has the correct value? Volatile turns that off. And if you want to know more about that particular optimization, come to me in office hours because I can tell you all. Because I've implemented it before. Yeah.
Is there a system call that I can use to disable all the CPUs but one? To avoid wasting
Well, depends on the OS. OS wants me, man. I believe BOS has a stop CPU system call. I believe, if memory serves me. I have not used BOS a lot. I use it for a very small period of time in the CS club because I was bored. Yeah, I'm pretty sure they have a stop CPU. And I'm not sure completely, but that many of them let you stop the last one. Alright, anyways, let's move on. Or before you get me going down the compilers and architecture rants. I don't want to do that today. Alright. So, we give you threads, that gives you race conditions. So we give you synchronization primitives to solve the race conditions, and now you get deadlock. There are different strategies at preventing deadlock in your code, as I'm sure you noticed in OS 161 doing A2A, that race conditions and deadlock are very, very hard to solve, and that's for a simple problem. What was it? I think I mentioned this the other day in class, but Google's actually made this like race condition detector for programs, and they actually ran it on the Linux kernel, and there was over 300 race conditions in the kernel. And that kernel's been out for a very, very, very long time. It's hard to stop these things, but some of the strategies we have for deadlock prevention are, of course, no hold and wait, which says that you, of course, are not allowed to own anything if you are waiting. So it's an all or nothing acquisition. And then there's resource ordering, which you must acquire the resources in a strictly increasing order. So advantage and disadvantages of no hold and wait.
You have to implement try acquire.
Yeah, that's a disadvantage. Any other disadvantages?
Is that you never have a deadlock.
Well, that's an advantage.
Oh, disadvantage. Sorry.
Yes, obviously the advantage is it works. It might have been a trick question. Yeah.
It's quite slow because you have to get a bunch of plots and release them if you don't get all of them.
Yeah, it can be a little bit slow because if you have 100 things that you need to acquire, you have to acquire the first one, try to acquire the second one, and if you can't get that one, you release the first one. So you're going to be looping and looping and looping until you actually get all 100 resources at a time. That's quite expensive. Now you might be thinking resource ordering is the answer, right? Well, sure, if you've got 2 or 3 things. But what if I'm trying to acquire 1,000,000 different resources? Well, then I'd have to sort it. Guess what the best performance for sort is? You're all taking 341, right? You remember that. To be fair, I once worked with somebody who fully believed that he had come up with a sorting algorithm that ran in linear time, and it was comparison-based sorting of strings. Yeah, they weren't from here. Let's just say we had a pretty good laugh about that one. All right, obviously the advantage is, hey, there's no deadlock. Disadvantage is that we have spinning when we actually try to get all the resources. And I'm sure if you think about this, you can actually come up with some other advantages and disadvantages as well. But those are the big ones. Let me see. In the interest of time, and I don't want to give you every problem that's actually here, I'm going to skip this one, which is just thinking about what problems need synchronization. And again, these slides are online, so if I skip over something, don't worry. After talking about threads, we talked about processes, which is, I really hope you actually tried A2A, so that when you get to the exam, you'll be like, wow, I know what a process is, maybe. So remember that processes, a lot of people, they're thinking, oh, that's the program. No, that's the execution environment created by the operating system for the program to run in. It is the address space where we store, the code, the data, and the stack segment. It's the thread array of all the threads that belong to that process. And of course, that it's got a PID, and it keeps track of its parents and its children, and it also keeps track of things like the files it has open, which we haven't talked about, but it does a whole bunch of things. Now, we isolate user processes from the kernel, and the reason why we do this is we don't want user processes to have access directly to the kernel, because anytime a user program can access data structures in the kernel directly, they can bypass the security that's offered by the kernel and just, oh look, I want the passwords. Hey, there's the tree for the file system. I'll just go play with it. We don't want that to happen. So for security reasons, we actually isolate user processes from the kernel. And for abstract design, because when my computer does an update, I don't want to have to download a new copy of something, which is why my previous Mac, I left it at Mavericks until 4 months ago, because I had Adobe CS5 on there, and it does not like some of the changes that Mac made between Mavericks and today. So that's a problem. You don't want that to happen. You don't want the user to have to buy a new copy of their software every time you change the OS. So for good abstract design, we isolate the user programs from the kernel. Now, how we do this is we don't even let the user programs call kernel functions. They're completely abstracted. The only way that a user process can get the kernel to run code, as I hope you are all familiar with, is through a system call. The system call, remember, is going to raise an exception in MIPS, or, well, an exception on a regular machine as well, with a regular OS. And on MIPS, we have to be able to tell the operating system which system call we want it to do and any parameters that it needs. We do that through registers stored in the trap frame. Now, for OS 161, we are going to put into register V0 the system call code, which is a part of the kernel's application binary interface. That is some headers that contain nothing secret, but are required for the user programs to actually know how to make the kernel do anything. And then into registers A0 through A3, that's where we would put parameters if we have them. And then finally, in MIPS, we've used the assembly instruction syscall to raise the exception. Now, once the exception gets raised, now remember, in MIPS, all interrupts and exceptions are actually treated as exceptions. So when the exception is, the syscall is executed, the exception is raised, the CPU stops, and it's going to execute common exception. And it knows where this is because the CPU has this thing called a trap table, which contains the address of the high-level handler. And by high level, I don't mean like C, I mean we don't know what this is yet. When we execute common exception, we don't actually write common exception onto the stack, we write trap frame, because essentially that's what common exception does, is it's going to say, oh, exception, I need to save the state of the user program that was running before I even tried to deal with the fact that an exception was raised. So, because we are now going to be running in kernel mode, because when the exception is raised, we switch from user privilege to kernel privilege, we need to be putting things on the kernel stack. So at the beginning of common exception, we are going to switch to using the kernel stack for that particular thread. And then we save the trap frame, which is every single register, even the special ones like low and high. Once we've saved all the registers, we are in kernel mode. Our interrupts are also off because we don't know what's going on just yet. Then we call MIPS trap. MIPS trap is going to figure out what type of exception it is. If it is an interrupt, we leave interrupts off because we want to respond to interrupts for hardware very, very quickly. And if we keep letting interrupts happen while we're dealing with one other piece of hardware, we're delaying and delaying and delaying. And the user program was like, hey, what's going on here? I didn't do this. Whereas with every other kind of exception, it is something the user program did, so we're okay with interrupts being turned back on. So if it is a system call, so type EX sys, we call syscall, that dispatcher that you had to add to the switch statement, and it will call the appropriate system call function for there. Remember that the return values, there are two, not one, we put into registers at V0 either error code or the return value, and into A3 we put either success or failure. And success is not 1, success is 0. So that's processes in a very quick, 3-minute nutshell. Yeah?
Two things. One, you know how you were lying to us earlier in the course about there being like one stack? Should
Yeah.
we just discard that for the exam, or should we, like, if we're asked questions about like threads, should we put ourselves in the headspace of earlier this term?
We are very explicit on questions like that.
Okay.
Yeah, that's something we're not going to be ambiguous. And generally speaking, we won't say, oh, just draw the thread stack for this particular case. We usually ask it with respect to processes, and the second you see processes, you should be thinking the truth.
Okay.
Or closer to the truth.
Yeah. And let's say I'm a 246 student, I'm leaking tons of memory, and I call like exec v. Will that leaked memory still be an issue in my new program that I'm running in that process?
Okay, so exec v and leaked memory. So the leaked memory is with respect to the old program's address space.
So we make a new address space.
Exec v links to new address space and tosses the old one out. So any memory that was leaked in your original address space doesn't matter. Yep. Which is why a lot of people write programs and just don't care about memory leaks. My friend's username is actually leaking memory. It's always fun when he applied to jobs. That's not an email address you want a potential employer to see leaking memory. Yeah. So for interrupts, we're not going to worry about that itself, but it's inside of, I think, main bus interrupt. You'd have to actually take a look. Don't worry, I'm not going to ask you about that. I only care about it with respect to memory and system calls. We didn't talk too much about hardware. Yep. All right, so the number one thing that we like to do when it comes to processes is ask you to draw the stack. So this should be something that you have memorized. It's a pattern. You should be able to spit this on the paper like that. It should be like an easy 12 marks, right? So draw the kernel stack for a running thread that has been preempted.
Yeah. That's why it's
Alright. So instead of getting one of you to tell me the answer, why don't you all tell me it all at the same time? What's the first thing that happens? And then? And then? And then? Okay, timer handler. And then what happens after the timer interrupt handler? And then? And then? You got it. It's that simple. Just memorize it, right? Now I know that we have not talked about anything that happens below main bus. So if we want you to call something below main bus, we will tell you what it is called. We will explicitly state it. Yep.
So you would tell us what yield is called something.
We will say that the timer interrupt is handled by timer interrupt handler, in which case you'll do timer interrupt handler or whatever we specify, followed by yield switch. We don't expect you to know how the hardware works. Yep. No, the reason why there's no memory leaks when you go call exec v is because we destroy the old address space and we create a new one. Which means all of the memory that had been assigned to the original process should be destroyed. Yep, and the operating system knows all about it and all of the memory that is still in there. All right.
So if you're running this call and then interrupt happens on the parallel stack, what changes? Like if there's crap not happens?
Well, it's a good thing I got more of these in here. Let's do a couple more. How about that? All right. Here's one for you. The user stack of a process that calls for. User stack. Alright, I'm not giving you much time to solve that one. Obviously that was a trick. Make sure you indicate that that process has been doing something prior to the call to fork. You can do that with ... You can write other crap here. I don't care. You can draw some funny rabbits chasing some pancakes. I don't know. It's so rare for you guys to draw in exams anymore. Like when I was in undergrad, that's like a total thing we did. Everybody drew all over every exam. And like as I've been here for the last like almost 20 years, like the number of people that do that is less and less. So here I'm telling you, you can represent other things with pictures.
Is there not a stack frame for like this call?
No. No.
How does this go to the kernel stack, or how does it accept
The exception is so forks implementation. The syscall assembly instruction is actually a part of fork. Yeah. All right. Now, if I asked you to draw, let's not do this one, the kernel stack for a process that calls fork. You of course know it's trap frame, MIPS trap, syscall, sysfork. This is something you should have memorized. Or hopefully you remember what it was from actually doing A2A, right? And you had to do a stack trace. You're like, oh my God, what's happening? All right, now let's put this all together. So we want a kernel stack for a process that calls fork and is preempted during sysfork. Now, instead of giving you a moment to look at it, here we go. We're going to take our preemption stack and our stack that we had from fork, and we get to put them together. So we were in fork, so we've got trap free mix trap syscall sysfork. While executing, sysfork, we got a timer exception. So we get another trap frame, mix trap, main bus, timer, yield, switch frame. Some rules. You cannot have two trap frames back to back. The reason why you cannot have two trap frames back to back is because interrupts are turned off before the trap frame is put onto that stack, which means that you are not receiving any exceptions or interrupts, and they do not get turned back on again until at least halfway through MIPS trap. So each trap frame must be separated by at least a MIPS trap. If you see two trap frames back to back, there was an error in the kernel, a bug. Yep. I believe, and memory serves me, that while we are restoring the trap frame, we actually briefly turn them back off again. Yep.
What is like common exception?
So common exception is actually what produces the trap frame. But instead of actually stating common exception on the stack, we write trap frame, because that is actually the thing, that's its stack presence, is putting the trap frame onto the stack. But technically speaking, that's common exception. And our TAs are aware of that, and it's sort of okay. All right, yep.
Just double checking, backtracking a bit. So if thread is preempted and there are no other threads, we go all the way to interrupt on the timer interrupt handler, but we don't have anything below that on the stack, right? We don't have thread below thread switch.
So for what's this? Repeat that again?
So when a thread is preempted, but there are no other threads, so
Yes.
the kernel stack, we wouldn't have thread below thread switch.
So you'd still call, like, it really comes down to the implementation of the OS. I believe in OS 161 you go all the way to thread switch, but no further. Yeah. So it just depends, where do we actually call the scheduler? Because it's in the scheduler where we would realize, oh, wait, there's no other threads. And in OS 161, our scheduler is called in thread switch. So if you are going to keep running after the supposed preemption, you would notice that inside of thread switch. But it depends on OS implementation. So we are very explicit on the midterm if we want you to answer the question with respect to OS 161 or not. This level of discussion is way deeper than we got with them. We don't expect that you've been playing around in like random functions. I expect that you did the assignment while looking at the bare minimum of OS 161's code as possible. All right. So I have another problem and I don't have the solution in here. Take a minute. So I want you to draw a tree of processes that shows how one process, forks other processes for this little code snippet here, and indicates that when that program completed or that process completed, what program was it running? So take a couple minutes and think about how you would do this. And I will draw the answer on the board for this one. Use edges to indicate which fork spawned them.
When you say execute program E, is there like additional code that makes your assembly explicitly happen when you do fork?
So you can assume that program B exists. I'm not. I just haven't given you the code for B, so it doesn't matter. All right. So you've had a minute to think about it. So I'm going to draw the tree on the board and just kind of walk you through as we go what's going on. So we start with some process. And I'm going to give them arbitrary process labels for now, just so that we have some means of keeping track of who's who. So this is process 1. And process 1 in program A calls for fork A. That's going to create a new process. This process. Now you know that both process 1 and process 2 return from fork A, which means both of those processes are going to execute fork B. And this is where the numbering system is just a rough labeling and not a specific order. So now I have how many processes, so I had 2 processes returned from fork A. How many processes returned from fork B? 4 processes. So all 4 of these processes now call fork C. So this calls C. 5. This one calls C. Number 6. This one calls C. There's 7. And that one calls C. So there's number 8. So 8 processes return from fork C. And now all 8 processes execute the next line of code, which is exec B, which means now all 8 of these processes are now running program B. All of them. And I will take a photo of my very hastily drawn diagram and try to post that if I remember. All right, so we've got about 8 minutes left, and I'd like to move on from processes here because there's still more topics, right? So, there's lots more questions in here, by the way. After we talked about processes, and the last topic that's on your midterm, of course, is virtual memory. Remember that we use virtual memory to isolate processes from each other, but also from where they live in physical memory. We are looking at how efficient are our implementations. We really care about that. How much extra space do they require in order to actually do the translations? How much time does it take? And we also care about things like, does it introduce any internal or external fragmentation that could pose problematic in the future? There are lots of techniques, and you are responsible for dynamic relocation, segmentation, and paging. I know it's not listed here. So remember, dynamic relocation. This is, we have just one limit and one relocation value for each process. We require that each process is contiguous in physical memory as one solid chunk. So if I have 4 gigabytes of available memory, and every process uses the maximum amount of virtual memory it can, and since we're only using 16-bit virtual addresses, the maximum number of processes that we could fit into memory at that time, you take the amount of physical memory, you divide it by the maximum size of virtual memory, we could have a maximum of 2 to the power 16 processes running. Yeah.
So we don't care about how much memory the kernel uses.
Pardon? We don't care about how much memory they're actually using?
The kernel uses.
No, we're going to pretend that doesn't exist right now. When we return from the midterm, we'll talk about the kernel. For now, we'll pretend it doesn't exist. All right. So, if we have a virtual address that is equal to the limit value in the MMU, what does the MMU do? Exception. Remember, we do zero-based addressing. This is not CS350. This is not MATLAB. Although I've heard they've switched it to Python. It's bizarre. All right. Let's skip over that. Segmentation. So just very quickly, we're not going to actually do this problem here. I want to do a multi-level paging one instead. Remember that for segmentation, there are different implementations. If we ask you a question about segmentation on the midterm that is specific to how it is implemented, we will tell you whether you are using a table-based or a register-based implementation. But either way, the actual translation is the same. You extract the segment bits to identify which limit and relocation value you need. If then the segment offset is less than the limit, it is within the segment and therefore valid, and you add the relocation to it and you're done. It's a small extension on dynamic relocation. So there's a problem there, a few problems actually. And then there is some problems in here on paging. But the problem that I wanted to do was another request. And I know that some of you have been trying this problem and posting your answers on Piazza, but I thought let's actually go through it. So there's a multi-level paging one here. So from our last handout, we had 64-bit physical and virtual addresses. And so you don't have to recalculate all this crap again. We have 20 bits that are set aside for the page offset because we're using page size of 2 to the power of 20. And each individual page can fit 2 to the power of 16 entries. We ended up having 3 levels where I left it out as 12, 16, and 16. Now you could make them more roughly even, but I just do fewest in the front and full in the back. All right, so we asked you then in the handout to, if a process only used from 0 to 2 to the power of 27 minus 1, how many valid tables existed at each level and how many valid entries would there be? Now let's expand upon that to 58 entries this time. So I want to show you the answer and kind of explain how I got it. So here's the answer for 58 instead of 27 bits. So the observation that you make is that if we are using, if all of our valid addresses use the lower 58 bits, then only the highest 6 bits are always 0. Which means, well, at the root, we only ever have one root to this tree. So number of tables at level 1 is always 1. It doesn't matter what the problem is, this is always 1. There's only one root to our tree. How many valid entries are in it? Well, we are using 6 bits. 6 bits are non-zero, which means there are 2 to the power of 6 valid entries in that table. And in that level as a whole, there's 2 to the power of 6 entries, valid entries. Now, if there are 2 to the power of 6 valid entries in the directory, each one of those valid entries points to a page table, which means at level 2, there are 2 to the power of 6 tables. And since all 16 of those bits are in use for valid entries, we have in each table 2 to the power of 16 entries, i.e. all of those tables are full. And then the total number of valid entries across that level, you take the number of tables, you multiply it by the number valid per table, and that gives you 2 to the power of 22. Which means there are 2 to the power of 22 tables in the next level. So we have 2 to the 22. They are all full, and so the total number of valid entries is 2 to the power of 38. So hopefully for those of you who struggle to understand how we did this problem before, this table will hopefully help you see a little bit better how we did this. All right, there's only a couple minutes left, so a couple things I want to say before you go. There are more questions in these slides than we have gone over. I also, if you're struggling with the virtual memory, I have posted the virtual memory guide, which has formulas and examples on how to use all of the formulas. So do check that out. The other thing I want to say is, of course, good luck on Wednesday. I'm sure you're all going to do just fine. And then on Thursday, I know you're all going to be tired and exhausted and wanting to go on some kind of sugar high because it's Halloween and, free candy, right? But we will have class on Thursday, and on Thursday we're going to go over A to B. So, incentive.